In today's videos, we're going to look at some issues of PID control that specifically relate to implementation. That is, how you use PID control in a robotic system. We're going to first talk about some hardware issues, and then we'll talk about some software issues. Specifically, in the software part of the videos, we're going to talk about the issue of tuning. Tuning is the process by which we find good values for the proportional, integral, and derivative gains in our PID controller. To begin with, let's take a look at some hardware issues. We've seen previously that feedback control requires a sensor in order for it to work as feedback control. But it doesn't work for you to use any sensor hooked up in any way. In order for feedback control to work, the sensor has to be hooked up within the system in the correct way. Let's take a look at how you have to hook up the sensor in order to get feedback control to work. In order to try and help you understand how a sensor has to be hooked up within a system in order to get feedback control to work, I want to start by showing you an example of the very earliest machine built with feedback control. This machine doesn't have a sensor in our traditional understanding of a sensor as a device that converts a physical property into an electrical property. But this device does, in fact, achieve feedback control. It was invented by James Watt in the 18th century, and it's used for controlling the energy produced by a steam engine. When a steam engine begins to run too fast, you can slow it down by opening a valve to release steam. On the other hand, when the steam engine is running too slow, you can speed up the engine by closing a valve in order to make the engine run faster. The fly ball governor, also known as a centrifugal governor, was designed to use feedback control to achieve a constant speed of the steam engine. Let's look at some of the key parts of the fly ball governor. Over here we have the valve that can be opened and closed to make the steam engine run faster or slower. This valve is attached to a rod which has a fulcrum right at the center of this rod. The other end is attached to a collar which is placed on a rod here, and this rod is attached to the output of the steam engine. So as the steam engine turns faster, this blue rod spins faster as well. Now, this collar, which is attached to the valve, is also attached to a couple of steel balls on these rods down here. These steel balls and the rods they're attached to are also attached to the shaft, which spins faster or slower as the engine spins faster or slower. Let's watch what happens when this device runs. As the steam engine spins faster, these steel balls fly out away from the center due to the centrifugal force, and this in turn causes the valve to close. As the engine spins slower, the balls sink lower, closer to the center rod. That causes the valve to open. Now, there are a couple of keys that are important to note about this device that tells us that it is using feedback control. Note that it doesn't look like this device uses a sensor. However, the steel balls on the rod here serve as a sensor because they give us an indication of how fast the steam engine is running. The important key that tells us that this device uses feedback control is that the sensor that is, these steel balls, are attached both to the device that controls the steam engine, the valve, and it's also attached to the output of the steam engine, this rod which turns faster or slower based on how fast the steam engine is running. When we implement feedback control in any robotic system, we need to make sure that we follow this rule as well. The sensor that we use needs to be connected into the controller device, like our PSOC, and it also needs to be physically connected to the actual thing that we're trying to control. For example, if we are trying to control the position of the slider on the motorized slide potentiometer, it's important that our sensor, the potentiometer, is physically connected to the position of the slider. I'm going to show you a couple of examples of this. Here's the diagram that we use for our motorized slide potentiometer in class. Notice that in this device, the sensor, that is this variable resistive material stretched across the device, that sensor is physically connected to the position of the slider. As the slider changes its position, the sensor changes its resistance. When you're working on some engineering project and you have to buy some motors for your project, you will generally have the option to either buy a motor as is or a motor with an encoder. I'm showing here a picture of a motor with an encoder. This is the encoder here on the back. It's difficult to see just in this picture, but if we would take this device apart and see how that encoder is attached to the back of the motor, we would notice that the shaft of the motor goes all the way through the motor and out the back. The shaft goes through the motor like this, and the encoder is attached to the shaft right there. This is a key important aspect of attaching a sensor to an actuator. Because the encoder is attached to the shaft of the motor, that means that our sensor is sensing the thing that we want to control, that is, the motion of the motor shaft. It's vitally important that the sensor be attached to the thing that we're trying to control. Otherwise, we won't be able to achieve feedback control. You can kind of see that this is true if you think about what the arrows represent in our feedback control diagram. Here, the output of the motor is the same quantity that is going into the sensor. And also, the quantity that is output by the sensor is what's being compared against our command. If we are giving the motor a command to tell it to move to a position, but the sensor is sensing something different than the actual motor position, then our control diagram will not create a complete loop. Let me show you some examples of this case. Here I'm showing a video of a conveyor belt that I have in my lab. The conveyor belt has a knob that I can turn to increase or decrease the speed of the belt. This knob is very useful for me to control the speed of the belt, but I cannot do feedback control using this setup. The reason is that the knob is not connected to the actual belt movement. The rotation of the knob is done by me with my hand, not by the motion of the belt. That doesn't mean that this is not an example of control. It is an example of control, speed control, but it is not an example of feedback control. This is what we would refer to as open loop speed control. It's not feedback control because the potentiometer here, the sensor, is not physically connected to the property being controlled, that is, the speed of the belt.